So let's dive right in. John, what problem were you trying to solve? What was the big picture?
Well, our customer had a medical device for us to reprocess, and this medical device was similar to a wire, and it'll have bends in it when they get it back for reprocessing, and they wanted us to help straighten this device because the OEM device is a straight device, and so they need it to be just like the OEM device.
And for our audience, what does OEM stand for?
It's original equipment manufacturer, so it's straight new from where you would originally buy a product.
So OEM is synonymous with the original, the brand new device?
Yep.
Okay. And we purposely want to avoid naming the exact device that we work on. We don't want to tell what our customer name was. We just want to show you the solution to what the problem was. So to my understanding, they have this brand new device that people use, a medical device, it sounds like. And once it's used, a wire is bent. So they want to reprocess it, basically be able to reuse it, and they need to be able to straighten the wire. So what John designed is, from what I understand, a fixture that will allow us to straighten the wire. Am I correct so far?
Yep.
Okay, great. So let's see. Now that we understand the problem, could you show us what the final solution was? If you could show us maybe the top level assembly, which we will call TLA in this video. So if you want to spin it around and show us how it works.
Yeah, this is the final solution that we made. It goes on a rail, and so the operator in the reprocessing facility will move this carriage back and forth along that wire, and these rollers will interact with that wire. They'll be clamping on that wire and make little bends back and forth until the final bending is actually back to straight, because this wire has elastic properties, elastic and plastic deformation and elastic deformation. We want the final plastic deformation to be resulting in a straight wire.
Perfect. So would this be the time to maybe make the top level assembly transparent to show us a little bit of what's going on inside? And maybe you can show us the Google search that you conducted after that.
Yeah, I can make these transparent. So here's the rollers that we have clamping onto the wire. And this mechanism is like a toggle clamp mechanism. It's an over-center linkage crank slider mechanism. And so there's a latch that holds this handle that's in the back up in this orientation. However, when we're clamping, this little link in the middle will go over center with the red and the green linkages and click in right there. And it will be adjusted to clamp this half with that half really tightly. There's an adjustment screw there. So that's clamped. And it'll go back to this point the same time, the same place every time. There's an adjustment screw on the top so that the operator can adjust the force, essentially, of the straightening action so that the wire can be bent not too much, but not too little. And it's a little bit of an art until they have the process down. They'll make essentially a recipe. So they'll do this setting, this clamp setting, and then that clamp setting until finally the last process will result in a straight wire.
Perfect. So that was the solution in the very end. Now we want to take a step back and begin from the beginning again and start diving into some of the details. So how does a senior designer like yourself approach a design problem? Do you have any specific processes that you follow? And if you could break that process down for us, maybe in a visual way or show us some images, that would be splendid.
Yeah, well, the first thing that we got were requirements from the customer. So we got the size of the wire, the length of the wire, and that's essentially how long the rail would need to be that this carriage would run on. And then we got a number of cycles per day that factored in here. Also, then the next thing I did was to look at existing off-the-shelf devices or mechanisms that would accomplish this task as well. And no one is in this day and age is going to most of the time invent their own full solution from scratch or from no existing idea. And so the first thing that I do is just see what else is out there already. And sometimes the best solution is already out there. Sometimes you can't use what's already out there.
How come you can't use what's already out there?
So one of the things for this application was that a requirement was that there's two ends of this wire that can't be touched with these rollers. So they wanted to be able to insert this device into the rollers quickly without touching those, and that resulted in this clamshell clamping arrangement that allows the rollers to separate fast and then come down and clamp at the same location quickly as well.
Okay. And before we started the recording, you were showing me some Google images as to where you gather your inspiration. Could you show us that again?
So this is one of the off-the-shelf straightening devices that we tested for the previous project that we did. That was a very similar project that was a little bigger type of thing that we were straightening. And this even is too big for that example, for that product that we were straightening. The total length of, just to give everyone an idea of how big this one is, this straightener is probably 11 inches, 10 or 11 inches total length in this, on here, in this sheet metal part. And those are probably 2.5 inch diameter wheels. So they're just too big for our application. There's a big V groove in them that's probably is like 1/2 inch wide wheels at least.
Okay.
And so we got that and tested with that, and there's like a kink that you can get in these really small tubes that they wanted to see if they can handle that. So these rollers are too big and too spaced apart to get that kink out, and that's what we found out from testing the off-the-shelf product.
Okay, so from my understanding, it sounds like the customer presents a problem and you try to Google a solution that already exists to solve this problem.
Essentially.
You try to see if that's a clever thing to do. Don't have to reinvent the wheel. Order an off-the-shelf material. It's just something that's already made that you can just purchase and test in-house. You see how well it performs, and then what's the next step after that?
Well, the next step would be so for this application, we created a prototype that replicated this roller setup and didn't have the quick movement because it was a early prototype stage, just to get the sizing right. And the prototype size, instead of being like 11 inches long, the prototype size was like 4 inches long with probably like 3/4 inch wheels. So we did some estimation, some quick testing with smaller wheels, and we 3D printed an actual prototype that we could straighten with, and they liked that.
Okay, so when you say you're basically updating the customer along the way. Is that what's happening? Okay.
Yep.
And you changed the wheels, so it means that you had to go and order some more off-the-shelf components and create smaller wheels, buy them and insert them or assemble them on the 3D printed part. Is that right?
Yeah, well, I ended up 3D printing the wheels initially, and then we've had some machined in order to have those metallic and rigid instead of somewhat pliable when you're getting into bending metal with something else. So the 3D printed parts were good for an early prototype. But then we went through and ordered some custom metal wheels with off-the-shelf bearings, off-the-shelf pins and screws to put it together.
So you mentioned Were you working on this project solo, or was there other help? And if there was other help, what did the other help with?
Well, I worked with my project manager and with some other engineers, some junior engineers that helped with the designs. So it's definitely a team effort in a lot of this. Very early, it's sometimes just me or someone else with input from somebody else as well. But
Now, what I wonder is when you start diving in and testing these hypotheses, do you ever write them down or you just keep them in your head?
oh, that's one of my major processes personally working on mechanical design is getting a notebook and sketching in it. An actual notebook on paper. There's just something about how the brain processes and puts ideas onto actual paper with actual pen. And I'm not sure even like a tablet can replace that. Like eventually you'd want, to share your designs with your team. And so a tablet, let's say, is easy to like take a screenshot of what you sketched, send it in a Teams message. But you could also just take a picture.
So tell us,
take a sketch.
of course, tell us when did you use the notebook for the first time in this project and for what purpose?
Well, I think I used the notebook to sketch out just overall ideas, and I think, this is the page that I started off with. We got some pictures of rollers, some pictures of how we're gonna like move the rollers apart and together. There was actually a previous notebook that had that older initial prototype. I don't have that with me because that was like a year prior to this actual fixture. But there were some other sketches in that. But
I'm gonna put it in the camera. So this is we're looking at this page over here.
both of those pages
Both of
are
those?
related to this project.
Okay, it's probably all confidential. We can't show you guys this. Or is it confidential?
Well, the title up there.
Oh, okay. We can't show the title. And tell us what goes through your mind as you're doing these sketches, because I see a top view and I see an isometric view. What's going through your mind as you're putting this on paper?
Well, I'm hugely into the visualization part of mechanical design and mechanical engineering. You have to visualize what the end product might want to be, you might want it to be, how it should be, how it's going to be used. Like if it's going to be used by someone other than yourself, you still need to think about how they will use it. If it's going to be influenced or thrown around or impacted by something else, you have to try to visualize how it's going to be impacted or affected, like by weather. Or like if it's going to be out in the rain, you can like close your eyes and think of it having raindrops like come on it and wind. That's just an overall general example of that. But like for this example, these rollers are going to come together to clamp and then come apart. Like how are we going to do that? We decided we wanted to have them both come apart from the middle so that the customer could try to evaluate a straightness without removing it from the fixture. It'd be quicker to, instead of the least number of motions that the operator would need to take is always the best. So if we just had a lever, unclamp it. It's also for rotating the device to get all the bends out, but you can open the device and they could check to see if it's straight. So just think about that. Okay. And this isometric view is just an overall thought of what it would look like, just as a systems engineering type of view.
So going back to a question that I asked earlier, do you ever write down what your hypothesis is when you're conducting a test, or you just kind of go for it?
Yeah, you definitely have to have an hypothesis in order to have a path. Yeah, definitely.
It sounds like the first thing that you were testing is the appropriate wheel diameter, if you will, to straighten the shaft. Is that correct?
Mm-hmm.
To straighten the wire. But you didn't test, to my understanding, any of the clamp features. Is that correct?
That's right. Yeah, the first step was to make sure that this operation, as if these did not move up and down except for the adjustment, worked the way that they should. That prototype did have the adjustment, but it did not have this large motion of going apart and coming back together.
Okay. Because the big distinction between what you've designed here, the beautiful design, and the picture, if you wouldn't mind flipping backwards from Google Images, is that this has no motion vertically.
That's right.
It's
Yep.
standstill. So how do you go from this to what you had on CAD? That clamp motion.
Well, definitely some brainstorming and trying to visualize how you can get the wheels back to the same spot every time and make them come apart at the same time. And sketches and whiteboard sketches and CAD sketches. Just a lot of thinking about how it'll work. And one thing that I really like to do is to have a sketch that moves in SOLIDWORKS at that point. When you can do that.
You would make me so happy if you could show us one of those.
Okay, let's see. So I'll make a new part.
Would you happen to have the exact one that you used?
Well, let's see. You need some like dun 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 dun. Nice. Yeah, there we go. Perfect. So this project, this mechanism got to be so involved. We like to use master models when there's a lot of parts that interact with each other, especially if it's more complex, so that you don't have to go too many different places to more efficiently update a mechanism.
And to my understanding, a master model is having multiple parts under one part file. Is that correct?
Yep.
And then you can export them all, usually by save bodies command, correct?
Yeah, that's one of the ways to do it. And another way to do it is to insert this master model and delete, or essentially delete what you want, but there's a command that you can just keep what you do want. So that's another way to do it. Another way to use a master model is to actually make configurations with one configuration per part that you want to end up with. So those are 3 different ways that you can do that.
Okay, just to make sure that everyone's following along. So he's using a master model, and what was the next thing you were going to show us?
Well, we were looking for that sketch.
So this is a sketch that John explained he used to visualize how the mechanism would move, and the key word is move. What comes to mind is when a sketch can move, it's either unconstrained or it's a layout sketch, correct?
Mm-hmm.
So how do you go from that to having a solid in CAD? Because that's a big leap. Like, you have to understand how the faces come in contact with each other, how the forces transfer. I mean, there was a step in the middle from that idea to this. What's that step, right?
Yeah, I think the step, there's an understanding of how of a known mechanism that is the middle step, I think, in cases like that, because if you know how a certain mechanism works and you go, oh, let's just use that sort of mechanism and put it in there, then you don't have to do as much development in that design, I guess I would say.
And the customer ends up saving money because it's less engineering time and you don't have to reinvent the wheel. It's a proven mechanism that you know is going to work, but you still have to conduct some testing. Okay. Yep. Do you remember what that mechanism was that you borrowed from?
Well, I don't exactly. There's a really good site that is 501 movements.com. Gosh. $507. Dang it. Well, there's a really cool site called 507 Mechanical Movements, and this might not have been where I got it from, but I love to use toggle clamps, and it's very similar to if you go to McMaster, because we use McMaster, and go toggle clamps. It's very similar to this sort of toggle clamp here, a compact push-pull. Where you can see this middle member here that's kind of hidden by the others is curved, even though it's a two-force member, which means there's a pinhole on each end of a piece of material, a bar, and so the only constraint is the axis, and the axis, when you want to pull them apart or push it together, it doesn't want to stay in a certain spot except for just where the other pivots are. So those are used in four bar mechanisms, and it's used in toggle clamps. So this is a slider crank, essentially, linkage. So this is the crank mechanism, the crank part of it. This is connected to the huge lever, so one would lift this lever up, and this pivot point would rotate around this pivot point, which is hooked to the whatever the toggle clamp is hooked to. And in doing that, this pivot point moves to the left, and when this pivot point moves to the left, it also moves up. But when this pivot point moves to the left, this pivot point moves to the left because of this curved part. And in our model, I wanted to have a toggle clamp mechanism to lock this thing down. It's shown lined up with the center points here, but this actually goes over center and locks. And in order to have the space for these and get around this central bar, this needed to be curved. And that's just visualizing what is in the space and where you can have different parts.
Does this model have any motion? No, right? Because it's a part file?
This part file does not have motion. So if we go back to this assembly, nice. We'll open up that. There, open up that. Here's the mechanism that moves in the assembly. So it'll get latched right there, a little over center.
What causes the latch?
Well, this is just like a toggle clamp. The latch part goes over center. So when this is closed, of course they're not going to show it closed on here, but if we go back here, this latch going over center means that it wants to be either on this side of the center point or this side of the center point. And what I mean by that is this part is rotating on essentially the center of the circle in here. That's the axis. And when you rotate that, it moves the red part down and the green part up. When we rotate it this way, there's a certain point where these two faces touch each other, and the red part is linked to the bottom part here, and this pin, through this pin, and it doesn't want to go up anymore. Since there's still an upward component of that rotation here, since it's not the top dead center is right there, and it's not yet, it's already clamped. So that red part wants to stay down. So the red part wants to go down like this. This is an exaggeration because there's obviously a gap here. The red part wants to be down like that, or it wants to be down like that. It can't go like this because then it would go through, this part would go through the green part and the red part. So it just goes until it stops.
Okay.
That's the latch.
Could you show us maybe, is there a sketch that you used to visualize all this? Something that you started constraining and moving around, or?
Yeah, and I had help from another engineer here, Rhett, and he did a lot of this model. We worked together on this, so shout out to him. The sketch that, let's see, this was the sketch that we used at this point. So here's the J, and here's the points on that central rotating bar, and the endpoint and endpoint. And all we needed to do was make sure that this material is out of the way here. And this is essentially this is where the over travel comes into, or the over travel in the rotation of this middle link. There's 35 thou left between here.
Now, my question is, how do you delegate this to another engineer? Because you have to explain them the whole process, and isn't it just better for you to do it yourself? Walk me a little bit through that.
Yeah, luckily, a lot of the engineers here, basically all the engineers here, are easy to understand what another is trying to work on, trying to develop the concept. So if good reason to have a sketch in a notebook or a sketch in SOLIDWORKS, preferably both, is to be able to explain, like, here's where I came from, here's this is this, and now I'm here in SOLIDWORKS and I need you to finish it for me because I have to work on this, and maybe I'll come back or maybe I won't be able to. And if you have all that information for somebody else to run with, as if they came up with it, they could pick it right up. It's sort of like going through college, and the people who developed the engineering calculations and techniques were teaching you the class, because that's essentially what's happening. They're telling you that, well, then when I developed this turbine engine, this happens and this happens, so this is the calculation that you need to do. It's just like that. It's like when you're going through college. If you have the notes, if you have whatever calculations that you can provide it to the other your colleagues, they'll know what they need to, and they can always ask questions.
So it sounds like, please correct me if I'm wrong, it sounds like you do some of the more mechanism thoughtful work. You think about it in your head, you internalize it, you put it on paper, and then you show the more junior designer or engineer how to finish it out on CAD. So it sounds like this skill set of knowing how mechanisms work is more of something that senior engineers are better at. Is that right?
Yeah, it depends. If the junior engineer or like someone starting out just really had liked mechanisms growing up, or liked trying to 3D print whatever they want growing up, and maybe just didn't have the formal training, then maybe they'd be more inclined to picking that up right away and maybe have that experience. But if you didn't do that, then otherwise it's just the experience of developing things as an engineer. You learn more and you get to know more the more you do it.
When is it most useful to have a junior engineer to help you on a design? What makes the perfect junior engineer that you can hand off work to?
Someone that's proactive, someone that is a good listener, someone that documents things well, and someone that has the willingness to fail, but the willingness to get back up or keep trying. And those qualities are probably not necessarily engineering related, but they're good qualities for someone who's essentially kind of like an apprentice type quality.
Yeah, good character. Okay. What would you say was the hardest part for the junior engineer that you handed this project to? What was the hardest obstacle that you think they had to overcome on their own?
I think it was, for this part, it was making things fit in the space that it needed to fit. And since I handed it off without that much consideration as far as that goes, I think I had made a pocket for this linkage, actually. But it was the packaging of that mechanism as far as where things are going to go, and I think we changed this from a single shear to a double shear so that we didn't accidentally bend the pin out. It's good to have double shear when you can. When you're, for instance, in this, there's two plates on either side of this single plate that goes in the middle. So there's double shear on that pin. If there was single shear, then there's better chance that you would bend the pin if you got more force than you expected.
Okay, understood. Coming here to an end, last final questions. What was the hardest part about developing this mechanism inside SOLIDWORKS? The part that maybe gave you the most frustration, or yeah, because I'm sure frustration happens, right? Designing mechanisms. Okay.
Yep. I think the hardest part was keeping track of all the updates that needed to happen, since there's a lot of moving components here. And to be on the same page with your team is paramount if you're not the only one doing it. If you have a lot of changes to do and you want to get them done quickly, then you probably won't be able to do them all yourself. If you can have the help, it's really helpful. So keeping track of the updates with the team that you're working on. And it's really good to prototype as early as you can. So just having a sign off internally even for what this prototype would be, how it would work, a sign off that let's make this machined instead of just 3D printed. I guess the timeline, it was the hardest part on that, because there's a lot of complex components here, and we had some complications with using 3D printed parts in this sort of higher force application in a cantilevered scenario, with these parts hang off the side of these moving parts. These clear parts hang off the side and have a lot of force on them. So just like a standard insert, we're stripping out. So the metal parts, or the actual machine parts, that's sometimes a real challenge, is getting some machine parts.
If I were to design this, the part that would give me the most trouble is if you wouldn't mind going to one of the earlier parts of it would be the movement, because the sketches are frozen. So I would like to see, when I move things, how the faces come in contact with other faces, and how do you imagine that?
Sometimes well, for me, it's experience and also just my tendency to be able to visualize things well. But sometimes I can't visualize it enough either, and I just need to make a quick SOLIDWORKS sketch and have multiple bodies, and then you can do the multi-body export, whatever method that you choose, and put those back in an assembly and just move them back and forth so that you can see how they move when they're mated together. Sometimes you have to make sure that you have the mates right too. There was another project that we were working on that I think the incorrect mates were placed on it. I questioned my colleague, and we figured out, yeah, I think they were incorrect. We caught something that we otherwise wouldn't have, because it is in a virtual world. And if you don't have the constraints right, which are the mates in SOLIDWORKS, then you'll miss something. You'll mistakenly approve something as you're going through it.
Well, let me ask you this. How can you sniff out when there's an incorrect constraint?
It's visualization. It's thinking about how it'll move, looking at how it's moving and seeing if it will move that way. It's really handy to be able to move things in SOLIDWORKS. So if something doesn't look right, I don't have a definitive answer as far as that goes, except to just go through and think about how each part moves relative to the other parts and make sure that it's mated, connected to the other parts in the minimal ways possible. The problem that we had before was that there was essentially an extra mate keeping things together when it was possible to pull them apart. So because they could pull apart, it changes the whole thing. It's like setting something on a table and saying you can't pull that up, but you can slide it around. That's a surface, that's a coincident mate.
Yeah, there's not a fastener or anything holding it to the face.
Yeah,
right.
Yeah, you can slide it around with this remote. You can set that on a table, slide it around, but then you can lift it up. And this other thing, it was mated so that you couldn't lift it up, and that just changed how it worked or didn't work.
Amazing. Well, John, thank you for teaching us what happens behind the scenes when a senior mechanical design engineer is tasked with a problem to solve. Are there any last words you may have for our audience?
I think just practice as much as you can and fail and redo and keep trying, and don't go down one road because you really like it. Go down a road because it makes sense as far as the design goes. Well, in life too, but just think about if it makes sense or not.
Very thoughtful.